Do 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 do. Still working on the intro. Hi, everybody. Making up my own intro music today. I'm going to put my lab coat on, but I'm hoping that those both in Southern California and abroad, or on different coasts, can appreciate how hot it is here today and won't make me keep it on all day, or I should say all for the entire show. But I'll keep it on for as long as I can tolerate. How's that? How's everybody today? Hopefully well. Welcome, welcome. We've gone back to the old set. I think this was working out better for people. I've got the diagrams up here and I've got it copied here, so I think that was kind of the best way that I could both draw diagrams, have everybody see them, and not lose people here and keep on the questions as well. So again, hi everybody, I'm Julia. You're here at Fine Woman's Broadcast, Daily Science, and I had a lot of requests. Hi Lariat, welcome. I had a lot of requests for magnets and what are they, how do they work. So you request, I will hopefully make it interesting for you and help you understand something that you didn't know before. So, oh, excellent, excellent. So let's see, T. Shaw. I'm still trying to get better at first names. Thomas. Glad to hear that, Thomas. Hey, Paul's here as well. So glad to hear that, and hopefully this will only make it more interesting for you. So we're gonna do magnets this whole week. I've been trying to plan. Excellent, excellent. Great to hear. I'm glad you're stoked. I've got a whole week planned, semi-planned for magnets, talking about them in different ways. And thank you for the heart. So for anyone who's new here, I would love, actually, if you're new here, to give me maybe a thumbs up or type thumbs up, type something. But I would just do a brief introduction. And, oh, great, welcome, welcome. So what I ask here, I'll flip it around quickly. What I ask here is if things make sense to you, that's where you use the hearts, because that's the most immediate feedback I can get is the tapping. So thank you for that. I don't mind so much about the numbers, just to see that you follow me. And then the 42 I have here, if you don't understand me or you would like a different description or a different way for me to explain it, then just type either 42 or something in the comments, whatever you're most comfortable typing, just to tell me that you don't understand. And here, we'll get to these fancy magnets soon. Ah, thank you. I am trying to speak more slowly, and I've got some notes here, and I do rush down through the introduction, so I'm sorry. I'm trying to be better at that, and I get so excited about this stuff, so it is. I like the system a lot, so I get excited and I talk very quickly. Please remind me if I keep going fast, remind me to slow down again. I don't mind the reminders, whatever helps everybody hear. So again, my name's Julia. Today we're going to talk about magnets. The whole week we'll talk about magnets. And I thought I'd do a little introduction that includes some history, just a little bit of history, and as well as a little bit of how we use them. I am not related, not actually, but just inspired by Richard Feynman. Those magnets are dangerous if you allow young kids to swallow them, yes. Thank you. Hopefully I'm informative as well as maybe wearing the lab coat well. But the magnets, the ones that I have, no small children around here, and if there were, I would make sure that they didn't swallow those. So those are not good to swallow. So what is a magnet? That would be a good first question maybe. And I actually had, I think, Wikipedia's explanation up, and their definition of a magnet was a material that exhibits a magnetic field. So everybody get that? We're good? Understand it? Makes sense? Yeah. So what is a magnetic field? That's the other question. And it's really interesting because we have electric fields that we talk about rather more freely, maybe. We have magnetic fields that we talk about, and lots of other gravitational fields. But what is a field? A field is kind of a weird thing. Faraday does rock. Yeah. A field is a really weird thing. It's not anything that we can see directly. Hey Fred, welcome. I'm glad. We can't see them directly, but what we can see is the effect that it has on various other related materials that they exist because the Earth has poles. So no, the magnets actually don't exist. It's a great question, and that I will get to, how the Earth actually has a magnetic field to it, and why we have a magnetic field. And it has to do with the crust, or the core, excuse me, of the Earth and what it's made of. So before I get to that though, I will say, well, how do we know about magnets and how do we find them? And so a common thought might be, actually one of my thoughts was that there were pieces of metal that happened to be, small pieces of metal that happened to be permanently magnetized by whatever mechanism, whether it's the Earth's magnetic field, or what actually turns out to be the case is that meteors and things like magnetite, so these are pieces of other rocks that have fallen to Earth's surface, they have this permanent magnetic field. And oh, great, okay, yeah, gonna cover the basics. I'll try not to I'll try to keep everybody interested, but thanks for letting me know. Feel free to leave and come back. So the permanent magnetic fields, they were actually called lodestones. So these are these tiny pieces, and I have a picture here I'll bring up in just, yes, a permanent magnet like what you would stick on your fridge. So when I say permanent, I mean it will hold that magnetic field no matter what is, or rather, I should say, it has a permanent magnetic field no matter what the external situation is. You don't have to see the magnetic field by imposing another magnetic field. So that's amazing. Thank you for watching from Venezuela. So what I have here is a picture, actually. Aha, there we go. So I'm getting some hearts, so maybe people didn't know this or it's interesting. So it kind of looks like this murky black rock thing, and it's turns out that these are called, oh hey Scott, thanks for checking in. So it turns out these are called lodestones, and these are tiny, well, I say tiny but they vary in size, but those are little pins so you can get the scale. And it turns out that permanent magnets, things that you could stick on your fridge, those are actually, you have to actually make the magnets to have that field pointed in a permanent direction from the material, and that you can do either by heating it up very hot and letting it solidify in a very strong magnetic field, or, I don't speak Spanish, I wish I did, I would try, I speak a little bit of French though. But in that magnetic field, when you're making these magnets, that is actually, so the fridge magnets and things like that, you actually have to purposefully put these materials in a large magnetic field to make it a permanent magnet and something that you can stick on your fridge, or something that you can use to magnetize something else. So I don't know if you've ever, oui, je parle un peu de français. So I don't know if you've ever taken maybe a pin or a strong magnet with a pin and you've rubbed it in one direction and you've magnetized the pin. Right, so that's actually taking the magnetic field from a magnet and then magnetizing that pin. So you can do that as well when you're making a magnet for the industrial sizes, etc. So, hi from Arizona, and when you're putting them on your fridge, etc. So these lodestones were naturally occurring though, so this is many, many thousands of years ago, and these were actually how we made the first compasses. So there's the little history in there. We actually made our first compasses by finding, yes, so these are static magnetic fields, meaning, and they're permanent, meaning they found these little pieces from things like meteorites that had fallen many millions to billions of years ago, and they would use these in compasses because they saw that it actually was affected by the Earth's magnetic field. So that is, and they would also be able to pick up small pieces of iron and other things that are ferromagnets. So I can go back to the diagram board and write this down. Hopefully you can see this. These ferromagnets, thank you for the heart. So I think people are following me, trying to keep it slow and get to people's questions as well. And let's see. These ferromagnets, these are the things that you're used to seeing, like iron and these neodymium magnets that you see that I have here, and those are, here we go, ferromagnets. And if you can't see that, I am going to zoom in here. There we go. All right. not so great still, huh? Ah, I know what I did wrong. Ha ha ha. Let's come back up here. This is going to be better. Yes. So, we have ferromagnets. I'm sorry, I'm trying to, yes, thank you for reminding me. Ferromagnets. And I also now have my YouTube channel that's up, and I'm going to be uploading these. So if I'm still talking a little bit too quickly, then I encourage you to go back. Well, I try to keep these intro show sections a little bit shorter so you can go back to the replays and not have to sit through the whole thing. So I do the Q&A section later. So the contrast, yes, so I had this different background which was helping me contrast here. Thank you, Fred. I'm still working on that. So the ferromagnets, these are the iron, this is the things that you're used to seeing, as well as these guys. So these are rare earth magnets, and these, as you can see, have very strong magnetic fields and are attracted to one another or repelled, depending on the direction of the poles. And you love physics more than science. Physics is science. But and I'll take it. Physics and or science. It's all fantastic. Thank you for saying that. So the other quick picture I wanted to show here. Now maybe people are familiar. Yes, maybe people are familiar with these pictures here. Let's see if I can turn this down. Those are iron filings next to a bar magnet. So I didn't have iron filings handy today. I'm sorry. I'll see what I can do about that. But these are next to a bar magnet. And what that's showing is that field, this really weird thing that we can't see. We can see only the effect of the field. And, oh, great question. So the positive and negative. So yeah, these are all determined. It kind of looks, without a plus or a minus on that picture, right? It just looks kind of the same. It looks like these two big lobes. And so the plus or the minus or the north and the south pole, these are all relative measurements, right? So we kind of define relative to Earth, for instance, what is going to be a north and a south pole, and the way that we orient our hemispheres on a map. But really, it's just to say that we're going to have, there's no such thing, maybe you've heard of a magnetic monopole, or we have not discovered one yet, I should say. So these are theorized, but really in Maxwell's equations, which are kind of these standard equations of electromagnetic forces and fields, these actually, hey, so these have, yes, so I try to do this every day. So this north and south, again, it's just relative, and so we have these two lobes. So that looks like the field, and it's the iron that's taking the shape of the field. But the field is still this invisible thing. But here's the key. The key is that it will always, for the same iron filings and the same bar magnet, it will always take that shape. So it's always going to look that way, and it's always going to take that shape for that bar magnet, or any bar magnet of that strength and that size and shape, and any iron filings or other ferromagnetic filings. So that's these materials that are affected. So that's a lot about magnets, but I still haven't kind of told you what they are exactly or how you get these fields. Do all north poles point to Antarctica everywhere on Earth? Oh, so yes, so the Earth's magnetic pole is a fixed, so now if you're talking about just now as far as the next few hundred years, I'm not talking about thousands of years, because it does slightly shift. But if we're talking about just the next few years, the next few hundred, then yeah, our North Pole is about aligned, and I think it's actually supposed to flip sometime relatively soon, but I'm not, I'll get back to you on that one. That's going to be later in the week when we talk more about the Earth's magnetic field. Great question, though. Thank you, Jason, for asking. So, the last thing I wanted to say on this part of the show before, because again, I'm going to do some more stuff during the week, but the, no, so the shift would not occur like a big earthquake. Good question, though, Fred. So again, I'll find out more about that, because I don't want to get into some dangerous territory and say things I'm not familiar with, but yeah, so there is a lot of iron at the core, and it's molten, right? So it's moving, and that's your hint to how we get the magnetic pole that we have and the field that we have on Earth. The gravitational effect it has is just because of the mass and the density, and so how we're distributed, how it's distributed inside the Earth. But as far as the magnetic field and gravity, so they're not, can you reverse the magnetic pole? Yeah, so then we get down to, I'll give kind of an introduction and I'll get some great pictures for tomorrow's show. I don't want to kind of overwhelm people. But then you get the question of, well, how does this magnetic field, how does it form? And why are things called ferromagnets versus not ferromagnets? And why are iron and things magnetic while plastics and others are not? And the real answer comes from those electrons. So, I hope that's a good thing. Every question's accurate, I would say. North poles point to the south, not the north. Oh, I see. No, I think our North Pole it points to the north, but it's not, we call it true north, so it's a little bit off of what is directly North Pole. So it is about the same, but I think the degree, it's off by a few degrees. It's on the order of 5 or 6, but I've forgotten the exact number. But it's about the same. So true north and magnetic north are pretty close, but not exactly. Exactly, the axis tilts, so we're tilted a little bit, which also gives us our seasons. And not the distance, actually. So, yes, exactly. Yeah, it's because our Earth is tilted. So then the... Excellent, excellent. So thank you. So no, nobody here is dumb. Absolutely not. The magnetic north is south. Oh, so maybe I could be wrong about that. But that wasn't how I remembered it, so I didn't look up that specifically. Thank you for telling me. So I'll look it up. It depends on where you are. Yeah, oh, I see, that's right. Of course, yeah. Because, so just like the bar magnet, right? So we have these two lobes coming out. So that's what the sphere, the Earth, is going to look like. So we'll have these two lobes coming out. And so it's going to depend if you're at the equator, below the equator, or above the equator. So if you're above the equator, then we have our north pointed in the same direction. So then when you're below, you see the field lines are going to come out and meet. So that's, yeah, thank you for bringing that up, Jason. So I have to... I'll see if I can make a better map of that and maybe make for a picture tomorrow, and hopefully that'll make more sense. So then the last thing I'll say, the quick introduction as to why these metals or why these materials actually have a permanent field and how they can, when we create them, when we put them in a magnetic field, let them solidify, for instance, why we can get these magnetic fields, these weird kind of things we can't see but we can picture and see the effect of repeatedly at the same way. Not that I know of, but I'm happy to, I'll check it out. So the really cool thing is that all of these effects are coming from the electrons. So the electrons, which we've talked about, yeah, probably, I would imagine. So the electrons we've talked a lot about for a whole bunch of different things, whether it's arranging ions in water and splitting them apart, and those are carrying our electric charges, our current, right, for electrocution if you put your hand in water. We have those ions. So it's all these electrons. And the electrons have something called spin. And spin is to say that as the electron is, so this is a way to picture it. It's not exact, but you kind of have to, when it gets quantum mechanics and kind of weird, you have to make pictures that match the math. But again, just pictures. So I'll go to the diagram here. But the electrons are going to have this thing called spin. And the spin is essentially how that, for this picture, how the electron is spinning around its own axis. I do not wish to dumb it down. I hopefully only wish to simplify it as best I can, because I've always said before I don't like that word, because I think it's absolutely not dumbing it down. But anyway, so the electrons here, let's see if I can draw our charge. If I draw one big electron, and I'm going to draw a line just through its center here. So it's a most powerful magnet. So I don't, it depends on natural, if you're asking natural magnet or not, or the strongest magnets, there are very, very strong magnets in the MRIs. So when you go get an MRI, and again, this will be another topic on later in the week. These MRI machines, when you get either a brain scan or, oh, I'm sorry, Cindy, I missed that, what you said before, to your knowledge. But these MRI scans, things like that, that image your knee or image inside your body, those have very strong magnetic fields that are needed to see these very small effects of the actual nuclear spin. So not electron spin, but nuclear spin, and that's a similar idea to what I'm drawing here. So neodymium is a material, it's one of these rare earth magnet materials that I'm saving for the rest of the week, because I was looking up some of these materials. They've done some crazy things with magnets lately that I like that, Jason. So here, I've drawn a line quite badly, of course, but I'm getting better at the drawing. But if I was just drawing kind of down the center, so if that's one big electron, right? For a second, I'm just kind of, yeah, I heard about that, Fred, something about that, and you have a weird borderline, I think, also with Canada. But anyway, just to wrap this up, and I'll go more into this tomorrow. So these electrons, they're spinning kind of around their own axis. It's not an exact picture, right? Because at the quantum level, all this kind of stuff gets to probabilities. But the math that helps us give us these pictures, we have these electrons that are spinning, and if you arrange all of the atoms in a bulk material like an iron magnet for your fridge, and you arrange the material in this big strong magnetic field as it's cooling and forming, then all these electrons end up aligning their spins, so they all spin the same direction relative to each other. And that's really how you get a permanent magnet, like a magnet on a fridge. So it's the electrons inside the atom, or the outermost electron, just to be clear. So there's lots of electrons, for example, in an iron atom. But the outermost one is really what makes the big difference. And the outermost one having this spin, and all of these spins aligned, then what we can get is something like this. Oops. Oh goodness! I said my drawing's getting better, but it still needs some work. Thanks for bearing with me, everybody. So if we have this bulk material, then, can everybody see this? This is kind of what I'm trying to zoom in on. Then I'm going to draw these arrows here. If they're all kind of going in the same direction, like this, then what you get is a net, all of them pointing and arranging in the same direction. All along this bulk surface, and so that's how you get this magnetic field around it. So I'll try to talk a little bit more about that without getting too technical and strange. But yes, so they do ascend. Yeah, they use magnets to do the acceleration. So they will get these charged particles like protons, and they are affected by magnetic fields. And the other way you can create a magnetic field is using actually electric current. So I'll get into that also. There's lots of really cool stuff about magnets. So hi Ronan, welcome. So I'm glad somebody asked me this question. I think there's lots to talk about here. But the magnetic fields are definitely one way you can accelerate charged particles. So these electrons or protons, things that are charged, they feel that magnetic field, and you can use that magnetic field, like a moving magnetic field, or in a particular shape to accelerate these charged particles. So hopefully that was informative. And anyone have any last questions about this? I think as we go, magnets don't have to be iron or so metal. They pretty much have to be only. It's kind of it's not to say that the metal is what makes it a magnet or the other way around, but the properties of the metal are they're what allow these electrons to move in this way and align in this way. So the material has to have the properties, have to have the electronic properties. The electrons have to be kind of around the atom in a way to allow this to happen. So those tend to be, you have to be, ceramic, yes, of course, that's a good point. How much energy, I'm sorry, I missed that other question. How much energy to do that with the magnets? So ceramic magnets, yes. So those are another instance, so they don't have to be metal, but most of them, yeah, most of them are. But I'll look up what some of the ceramic ones are. Do they have can some? Yeah. So if you don't mind, actually, Jason, if you can ask me that other question in the Q&A, so afterwards, just because it's a little bit more, and I'd like to give a better kind of more in-depth answer without making this part too long. But just to answer your question, Fred, before I forget it, which I may be doing already, okay, great, thank you, Jason. So if you could remind me again, Fred, what you asked me about compass material, thank you. The strongest, I think the ones that are going to be most sensitive to the smallest magnetic fields, so that would be the ones that are going to feel so that would be the ferromagnets, and the ones that have this electron that can be affected the most, this most freely outermost electron. Those are going to be the ones that are more sensitive, so it's all about the material being sensitive to magnetic fields. So it will make a difference, but it might not make a life or death difference. Yeah, so a spinning motor is one way. So a motor in your car actually is an electromagnet. So we use an electromagnet that is how an engine will turn over. You run electricity, or part of the engine. So an electromagnet is one way. Yeah. Oh, hi, Justice. Welcome. Could you boost? Yeah. So electromagnets, and I'll definitely get more into this later in the week. The electromagnets will be you're making a magnetic field by a running current, or the other way around. But not excess mass. Oh, I lost. Oh, and how do we know the electron has mass? So the electric current, these electromagnets that you can make them for various strengths of magnetic field, depending on what you want to do. So, eating lots of flowers, thank you. So, making it more sensitive, you don't want to create something necessarily that has a stronger magnetic field than the Earth, because then that would dominate, I think, what you're trying to do. So you want these very freely moving needles here on your compass, so that it feels a little bit of a tug. But thank you, Justice. But to make a big electromagnet, I say big only because if you're using wires and typical things that we make electricity, or I should say circuits and components with, then that's just going to be bulkier and heavier. So I can't imagine a direct way to make them more sensitive, but there might be ways that do exist already. But yeah, so I don't know of any direct ways that are being used right now. And I think I'm talking quickly again. So I'll wrap this one up for now. Hopefully that was kind of a good introduction. Again, the whole week we can do magnets, so we can talk a lot about, I'm still finding out stuff as well, newer things, and to keep this going, and hopefully it's interesting. But that was, I think, for today. Yes. So thank you for both those comments. So the magnets, yeah, and when we use them in motors, for instance, we use electric energy to make these magnetic fields, and then the other way around, we can use magnetic fields to create electric energy and electric current. So, oh, thanks, Justice. Yeah. Hi, Gerda. Hi. So that was the brief introduction. The demos today were mostly here. I'll do one last just to see these weird fields. No, magnets don't create energy, so you can move magnets, and magnetic fields can create electric energy. So today we were to produce this energy. Oh, I'm sorry, I missed that last question. We have an energy question, so I don't want anyone to get confused. But these were my demos today, where we can kind of see these things acting a bit weird. And hopefully I'll give somebody a chance to ask another question. But if we can, so we can see that the field, although we can't see it, we can see the effect, and not only can we see the effect, but it will have a very predictable outcome repeatedly over and over again. So we can make like that. So I think I'm missing a few of the conversations, and I don't know if you're talking to each other or me, so I'm sorry about that if I'm missing it. But I'll go over Yeah, that's true. Don't wear that. Good point, Fred. So I'll go over when it comes to the motor. That was going to be a separate topic because the electromagnets is making a magnet using electric current is another way to make this magnetic field, and this was over unity. Oh yes, so that would be violating. I see. Thanks, Jason. Yeah. So when it comes to electric. Absolutely. Yeah. So electric and magnetic fields are very closely tied, and so that is why you can use electricity and electric current and to make magnetic or to create magnetic fields, and a changing magnetic field will in turn create an electric field, etc. So they're very closely intertwined, and they are very closely related. So when you get down to quantum, absolutely, you have to consider the magnetic fields as well, just as important as the electric fields. And I can talk even more about that as we go on throughout the week too. I know some of this was maybe review for some people or not for others. And as far as the over unity, when it comes to over unity, I think if you're talking about getting more energy than you put in, then if that energy isn't coming from somewhere else, then we can't violate the conservation of energy laws. So that may be a more in-depth discussion. But I'll wrap this one up to keep this one short. And right now, just teaching and writing. Yes, absolutely. So Versaida. So hi, I hope I said that correctly. Then what I do is I wrap the first section up, and then I come back and do a little bit more of a relaxed Q&A, just so that the replays are shorter and the episodes are a little shorter for people to go through the material. And I put them on YouTube so people can fast forward too. I'm starting that now. And excellent, Justice, nice to hear. So what would I research? So if you can ask me these questions to send in, I would love to answer them in the next section, but I would absolutely love to answer them. I don't want to seem like I'm brushing off. I just want to keep this one short for people. And thanks, Jason. Yeah, but I'm going to come back in just a few minutes. I just upload it, and then I come back for the second section, and we can talk about all of this, like the mass of an electron and research funding. Yes, please do. Twitter, absolutely. I'm on the same. Everything's the same. So finewoman.com. Twitter and Instagram is all Fine Woman as well. So please, yeah, short, try to huge. So thanks, Phil. So I'll, oh, my pleasure. And yes, thank you. And I will be back in just a few minutes, and we can discuss the deeper meanings of life and magnets, as well as research and funding. So down Periscope, happy science. Thank you, Justice. Thank you, everybody, for great questions, interactions, and for joining me yet again. And I'll be back.